Welcome to Hired in IT. Our mission is simple: help you build the skills that employers actually want. Whether you're trying to land your first IT job, switch careers, earn a promotion, or increase your salary, we're here to help. Every video is thoroughly researched and designed to make complex IT topics easy to understand. If there's an IT topic you'd like us to cover, leave a comment below. We may turn your suggestion into our next video. Turning IT knowledge into career opportunities. Last time we connected our on-premises network to Azure with VPN and ExpressRoute. Now imagine you've deployed 2 web servers in Azure. Confidently, you schedule maintenance on one of them, because the other server will handle the traffic. Except it doesn't. Every user was still connecting directly to the server you shut down. Within seconds, the application becomes unavailable. Nothing was wrong with the virtual machines. Nothing was wrong with Azure. The missing piece was a load balancer. Today, you'll learn how Azure Load Balancer prevents that exact scenario while giving your applications the scalability and high availability expected in production environments. By the end of this video, you'll be able to configure a zone-redundant Azure Standard Load Balancer that can lose an entire data center and keep running. Set up high-availability ports so your network appliances never become a single point of failure. And read health probes and load balancing rules well enough to stop the kind of multi-million-dollar outage I just walked you through. Think of a load balancer as a traffic cop. When one intersection, one server, goes down, the cop instantly waves traffic over to open lanes. Without it, every car just piles into the closed lane and nothing moves. Azure Load Balancer is exactly that, but for TCP and UDP packets. It's a Layer 4 distributor, no HTTP headers, no cookies, just raw network traffic. If you need to stick a session or inspect an HTTP request, that's Application Gateway's job, which we handle in Part 8. You've got 2 flavors of Azure Load Balancer. Public. Internet-facing, uses a public IP, sits right at the edge. This is for things like your customer-facing portal. Internal, stays inside your VNet, uses a private IP, and never touches the internet. That's for your database clusters, your internal APIs, your line of business apps that only employees see. Choose wrong, and you either expose something dangerous or lock customers out. I see this mistake all the time. Someone tries to point an HTTP-based application at an Azure Load Balancer. Don't. This LB lives at Layer 4. It doesn't read HTTP headers. It won't do SSL offload. It won't stick your session. Perfect for SQL Server on port 1433, DNS on 53, your custom TCP application, or a network appliance. For anything that speaks HTTP or HTTPS, you'll use Application Gateway or Front Door later in this masterclass. Use the right tool. When should you use each Azure networking service? Azure Load Balancer use when distributing TCP or UDP traffic across multiple virtual machines. Application Gateway use for HTTP or HTTPS applications that require SSL termination, cookie-based session. Affinity, or a web application firewall. Azure Front Door use when users are connecting from around the world and you need global load balancing, caching, or multi-region failover. Each service solves a different problem. Choosing the correct one is one of the most important architectural decisions you'll make when designing Azure applications. Before we go further, this is a checkpoint that mixes old and new, because that's how your brain hangs on to things. From Part 2, what's the default NAT gateway idle timeout? 4 minutes. Now, from the last few minutes, what 2 types of Azure Load Balancer exist? And which one would you pick for a customer-facing e-commerce site? public, because it's internet-facing, and internal, which stays inside your VNet. If you've been following old tutorials or you're inheriting a legacy environment, I need to be crystal clear. Basic Load Balancer was retired on September 30th, 2025. You can no longer create one in a new subscription. If you see a basic LB in your Azure portal right now, it's a ticking time bomb. You need to upgrade to Standard. There's a migration guide linked in the description. Here's why Basic is dead to us. Standard scales to handle significantly more backend instances, easily into the hundreds, while Basic had a drastically smaller footprint and no SLA. Standard offers zone redundancy across availability zones. Basic can't. High availability ports for network virtual appliances, NVAs, Standard only. And the kicker, Standard is backed by Microsoft's Enterprise SLA when you spread it across zones. Basic had no SLA at all. The choice isn't just clear, it's the only option left. You'll still find ARM templates, blog posts, and even paid courses that reference Basic Load Balancer. When you try to deploy them, the portal will just refuse. If an existing environment still has Basic anywhere in its load balancer settings, that's a red flag. Don't wait for an outage to prove the point. Raise a change request, follow the migration guide, and get onto Standard while you can still sleep at night. A single Standard load balancer can support multiple Frontend IP configurations, any combination of public and private IPs you need. That's how you build a multi-tenant environment without spinning up a new load balancer for every app. One Frontend IP serves your customer portal, another serves an internal admin API, and each one is wired to a completely separate backend pool. Next, we'll actually create one with the CLI. Drop into the shell and wire up your frontend. The as network lb frontend IP create command attaches a public IP. That IP must be a standard SKU, not basic. If you want zone redundancy, you pass zone 123 when you create the public IP. That front-end name is what you'll pin to your rules later, so pick something you'll recognize in a long list. Test yourself. What two requirements must the public IP meet before you can attach it to a zone-redundant front-end IP configuration? Picture a backend pool as a club list. You can add members by their NIC or just by IP address. Even a stopped VM stays on the list. It'll get a health check the moment it powers on. And here's the big one. None of these backend VMs need a public IP. The load balancer handles the inbound flow, and the VMs answer privately inside the VNet. Inside the portal, you open your load balancer, head to Backend Pools, and hit Add. First, you pick the VNet. It's got to be the same one as your VMs. Then you choose your membership type, virtual machine or IP address. Tick the VMs you want, click Add, and they're on the list. 5 seconds of clicking and your pool is ready. Without a health probe, the load balancer sends traffic to dead VMs and users hit timeouts. But with a probe, typically every few seconds, it taps your app's port. After a couple of consecutive failures, that VM is pulled out of rotation. When it recovers, the probe passes again and traffic comes back automatically. This is what stands between you and a 3 a.m. outage call. 2 flavors. TCP probe just knocks on the door to see if it's unlocked. HTTP probes walk in and ask for a specific endpoint, expecting a 200 back. One key difference: Basic Load Balancer does not support HTTPS probes. Standard provides more flexibility for probe configurations, so check the latest documentation for available probe types. For a pure TCP app like SQL Server, a plain TCP probe on 1433 is all you need. Over in PowerShell, you use add Azure Load Balancer probe config. Name it clearly. SQL probe is way easier to spot than probe 1. Set the protocol to TCP, the port to 1433 if it's SQL, interval to 5 seconds, and probe count to 2. I set them explicitly so nobody later wonders what's happening. 5 seconds between checks, and 2 failures to mark unhealthy. Let's lock this in. Before moving on, make sure this concept is clear. What does a health probe actually do? It continuously checks whether a backend application is responding. If the probe fails, Azure immediately stops sending new traffic to that backend instance. Once the application becomes healthy again, Azure automatically returns it to the rotation. Without health probes, a load balancer has no reliable way of knowing whether your application is actually available. That's why every production load balancing rule should include one. Here's the part that catches even experienced admins. If you forget to assign a health probe to your load balancing rule, Azure sends traffic to every backend instance, dead or alive. A crashed VM still receives connections, causing outright failures. The rule itself doesn't complain, it just keeps pushing packets. Make sure every single rule has a probe attached. This is the load balancing rule, the traffic conductor. It takes the front-end IP and port, like 1.2.3.4 port 80, and binds them to a backend pool of VMs using a health probe. Every new TCP or UDP flow gets hashed using a 5-tuple: source IP, source port, destination IP, destination port, and protocol. That hash decides which VM handles the connection. The rule is what ties all those pieces into one working system. Without it, your front-end IP just sits there with nowhere to send traffic. One command, one rule, everything wired together. The front-end port is what the world sees. The back-end port is what your VMs actually listen on. Change the back-end port to something different, and you've got instant port translation. Public port 8080 landing on internal port 80 without touching a single VM config. The other parameters pull in your front-end IP, back-end pool, and health probe by name. Run this, and your load balancer starts routing real traffic. Many people assume Azure Load Balancer simply alternates traffic between virtual machines. It doesn't. Instead, Azure calculates a unique value using 5 pieces of information: source IP address, source port, destination IP address, destination port, protocol. This combination is called the 5-tuple hash. Connections with different values may be directed to different backend servers, helping distribute traffic efficiently while keeping each individual connection consistent. If your application requires HTTP cookies or advanced routing decisions, Azure Load Balancer isn't the right service. That's where Application Gateway or Azure Front Door become the better choice. Lock in the distribution logic. What 5 values does the load balancer hash to pick a backend VM? Don't confuse these two. A load balancing rule fans one front-end port out to an entire pool of VMs, great for scaling. An inbound NAT rule gives each VM its own unique front-end port for direct access, like SSH on port 5001 to VM1, 5002 to VM2. That way, you can reach management ports without slapping a public IP on every server. Both live on the same load balancer, but they serve completely different purposes. Here's the portal flow. You go to your load balancer, hit inbound NAT rules, and click Add. Pick the front-end IP, set a unique front-end port like 5001, then point it at a specific VM's NIC and the destination port, 22 for SSH. Click Add, and now you can SSH into that VM via the load balancer's public IP on port 5001. Create another rule with port 5002 for VM2, and you've got managed access to every server without a single extra public IP. Clean, secure, and exactly what Azure expects you to do. Picture a hub-spoke network. Every packet from the spoke VNets is forced through a central NVA, a firewall or network appliance, by a user-defined route. Instead of one fragile NVA, you put two behind an internal load balancer with an HA ports rule. That single rule load balances every TCP and UDP flow on every port through whichever firewall is healthy. If the primary NVA goes down, the health probe catches it, and the load balancer instantly shifts all flows to the standby. The spoke servers never see a blip. This is the architecture that keeps enterprise networks running while you sleep. HA ports is a special load balancing rule. Protocol set to all, front-end and back-end ports both set to 0. That tells the load balancer, I don't care what port you came in on, just balance it across my backends. One rule replaces dozens of individual port-by-port rules. This only works on an internal standard load balancer, and it's designed specifically for network virtual appliances where you need to forward every possible protocol and port. But the floating IP flag is non-negotiable. Get that wrong, and you've just built a very expensive paperweight. This is the CLI command that creates the HA ports rule. Protocol. All with both ports at 0. That's the secret handshake. The floating IP true flag is the one that trips people up, but it's absolutely critical. Without it, the load balancer nats the source IP, and your NVA sees the load balancer's private address instead of the real client. That breaks any firewall rules keyed on source IP. Flip that flag, and the original client IP flows straight through to your appliance so it can do its security job properly. An Azure region isn't one monolithic building. It's 3 or more physically separate data centers, each called an availability zone. A zone has its own power, cooling, and networking. When a zone fails, a power outage or a cooling failure, only the VMs inside that zone go dark. The other zones keep running. That's the physical separation that zone-redundant services leverage to survive zone-level failures. Your load balancer, if configured correctly, simply keeps sending traffic to the healthy zones. Here's what a zone-redundant public load balancer looks like. Note: availability zones are not supported in every Azure region. Make sure you pick a region that offers them. You start with a zone-redundant public IP. This IP is hosted in all 3 zones simultaneously. The load balancer receives traffic on that IP and distributes it to your backend VMs, each deployed in a different zone. If Zone 1 goes offline, its VM stops responding. The load balancer detects that via health probes and automatically redirects all traffic to the VMs in Zone 2 and Zone 3. No manual failover, no downtime. Creating a zone-redundant public IP is one CLI command. Notice the standard SKU and the crucial Zone 123. That list of all 3 zones is what makes the IP zone redundant. If you omit zone or specify a single zone like Zone 1, you get a zonal IP that lives in only one zone. And that IP disappears if that zone goes down. Zone redundancy doesn't add a separate line item on your bill. Pricing is based on rules and data processed, not on how many zones you use. Internal load balancers can be zone redundant too. You configure a private front-end IP and mark it as zone redundant. That's it. All your backend VMs across zones see the same private IP, and even if a zone fails, the load balancer routes traffic to VMs in the surviving zones. Your internal services stay reachable through a single IP with no failover gymnastics. When you configure a health probe, the traffic doesn't come from your own resources. It originates inside Azure's network. The source IP is always 168.63.129.16, but never hard code that in your NSG. Instead, use the built-in service tag called Azure Load Balancer. That tag includes all the probe IPs and automatically updates if Microsoft changes the underlying infrastructure. Go into your NSG, add an inbound rule, set the source to the Azure Load Balancer service tag, and allow traffic to the port you're probing. That's all it takes to stop probes from being silently blocked. Let's lock in what you just learned. What is the purpose of a health probe? And what happens when a backend instance fails the probe? The health probe checks that your backend VMs are reachable and responsive. If a probe fails, the load balancer pulls that VM out of rotation instantly. No waiting for a second or third failure. Traffic is restored automatically once the probe succeeds again. When a load balancer doesn't appear to be working, don't immediately assume Azure is the problem. Start with the basics. Is the virtual machine actually running? Is the application listening on the correct port? Does the health probe report the backend as healthy? Is the NSG allowing health probe traffic by using the Azure Load Balancer service tag? Does the load balancing rule reference the correct Frontend IP, Backend pool, and health probe? Finally, use Azure Network Watcher and Azure Monitor to verify that traffic is reaching the backend and identify exactly where communication stops. Following the same checklist every time prevents hours of unnecessary troubleshooting. Today, you learned far more than how to click through the Azure portal. You understand the difference between public and internal load balancers. You know why Standard Load Balancer replaced Basic. You can build backend pools, configure health probes, create load balancing rules, and understand how Azure distributes traffic using the 5-tuple hashing algorithm. You also learned how high availability ports simplify network virtual appliance deployments and how availability zones allow your applications to continue running even when an entire data center experiences an outage. Most importantly, you now understand the architectural decisions behind these features, not just the configuration steps. That's the difference between learning Azure and thinking like an Azure solutions architect. Next in the Masterclass, Part 8, Application Gateway and Front Door for HTTP and HTTPS apps. We're moving up the stack from Layer 4 to Layer 7, where you'll handle SSL offload, a web application firewall, and global routing. Don't miss it. Subscribe and keep your Azure networking game strong. Remember, careers aren't built by watching videos. They're built by applying what you learn. Pick one thing from today's lesson, build it, document it, and share it. That's how you get hired. Thanks for watching Hired in IT, where we're turning IT knowledge into career opportunities.